Welcome back, everyone. Today we're going to continue our discussion of infinite sets. And I'll begin by outlining what I call the hierarchy of infinite sets. So my goal here is to start at this end, where I guess I'll start with the smallest sets. So this side will be small, this side will be big. And so the very smallest set is the empty set. That's the smallest a set can get. And then after that, we have finite sets. And we hopefully understand what finite sets are. So past finite sets, there's infinite sets. But, as we learned last time, there are different sizes of infinite set. So the first type of infinite set is sets of size, what we call Aleph 0. That is, size equals the size of the positive integers. And so again, you should think of this as being the smallest possible size of infinity, in a certain sense. Now we give the name countable to this whole collection of sets. Or, and I'll talk about why a little bit later, I also like to call this listable. I will note there is a tiny bit of disagreement about whether countable includes finite sets. For me, it definitely does. But be warned, someone might use the word countable, and they might actually be trying to tell you that it is this size. So if you're reading a textbook, you might want to flip to the beginning and see their conventions if they say something and you're not sure whether they're including finite sets or not. And so then there's this whole vast array of stuff over here, and rather uncreatively, we call this whole vast area, we call these sets uncountable. And I told you last time that one thing that's over here in the uncountable C is the real numbers. And the size of the real numbers we denote by Aleph C for the size of the continuum. And I told you last time that in a certain sense, the size of the continuum is strictly larger than the size of the positive integers. So the first thing I want to do today is I want to make precise what it means when I say that Aleph C is larger than Aleph naught. Or, as I'll write it, the size of R is strictly larger than the size of the positive integers. And then we're going to talk about sorting all of the sets that we know into their appropriate boxes. So I've told you where R goes and where Z plus goes, but what about Q? What about the set of irrationals? What about the complex numbers? And so on. So we'll talk about all of that and give that some attention as we go through this. But first, let's start with what is meant by saying the size of one set is strictly greater than the size of another. And so as a baby step to that, I'm going to define what it means for a set to have greater than or equal to size of another set. And I'm going to write down what I mean when I say the size of A is greater than or equal to the size of B. And I want you to think for a second what I'm going to write before I write it. And I'll remind you, in the last episode, we said that the size of A equals the size of B, and we defined that to be the case if there exists a bijection from A to B. What do I want to exist if I just want A to have size at least as big as B? And the answer here, and you can think back to a different part of the pigeonhole principle, is that we want there to be an onto function from A to B. While we're at it, let's define what we should mean by saying the size of A is less than or equal to the size of B. And so just to recap, we've described all of the relations between sizes of sets in terms of the existence of certain functions. So the size of A being equal to the size of B, that meant there was a bijection. The size of A is greater than or equal to the size of B. That means there's a surjection from A to B, or that is to say, an onto function from A to B. And to say the size of A is less than or equal to the size of B, that was to say that there is a one-to-one function from A to B. And all of these definitions are motivated by the first three parts of the pigeonhole principle. So this is what I call the pigeonhole principle part 1. And this is what we call the pigeonhole principle part 2. And this was the third one. Now, reminder, the pigeonhole principle actually had 4 parts. And as we've talked about before, the 4th part of the pigeonhole principle is never going to be true for infinite sets in any way, size, shape, or form. So these are the only pigeonhole principles that are going to be true for infinite sets. And what do I mean by they're true for infinite sets? In this case, I literally mean I defined it to be the case that these things are true for infinite sets. It was a theorem that these 3 things are true for finite sets, that is, that the size of A equals the size of B if and only if there exists a bijection between them. The size of A is greater than or equal to the size of B if and only if there's an onto function, and so on. So that was a theorem for finite sets. It is our definition of what those things mean for infinite sets. So it was really the genius idea of Cantor that you can't really talk about sizes of infinite sets without contemplating functions between them, and in particular one-to-one functions and onto functions. Now, I want to remind you that our goal here was to make precise the statement that the size of R is strictly greater than the size of the positive integers. And notice I have not defined that. But I now have all the pieces. Because if I know greater than or equal, and I know equal, then greater than should be greater than or equal and not equal. And strictly less than should be less than or equal and not equal. So here, in terms of our definitions from before, we say that the size of A is larger than the size of B, strictly larger, if the size is greater than or equal to, and the size isn't equal. But this is now sort of seeming tautological or like nonsense or like I'm not really defining anything. And I promise I really am defining something, but it'll look more like a definition if I rephrase what these 2 things say. So what am I really saying when I say that the size of the real numbers is strictly greater than the size of the positive integers? I'm saying that it is possible to write down an onto function from the real numbers to the positive integers, but it is not possible to write down a bijection from the real numbers to the positive integers. Now, I think it's important that I level with you here and point out that we've actually overdefined things. So what do I mean by overdefined? What I mean is I've allowed us to define things in 2 different ways, at least if we think we know what these symbols are and how they should work. Namely, having worked with these symbols for our whole lives, going all the way back to Mrs. Fisher in 1st grade class telling me that this was an alligator, and so the alligator always wanted to eat the bigger thing, so that was sort of how I remember this, and I still sort of mentally think of that even when I look at these things today. But we've been thinking about these things our whole lives. You should definitely expect that the size of A being greater than or equal to the size of B should mean exactly the same thing as saying the size of B is less than or equal to the size of A. So what I mean by saying we overdefined things is that we defined this above, and we defined this above, but we did so in a way where it is not at all immediately clear that this and this mean the same thing. Because how did we define it? Well, here we said the size of A is greater than or equal to the size of B. That means that there is an onto function from A to B. But then what does the second thing mean? The size of B is less than or equal to the size of A. That means there's a one-to-one function from B to A. So we really need this to be true. Namely, if A and B are sets, any sets, we need it to be true that the following 2 statements are equivalent. Namely, there's an onto function from A to B, and a one-to-one function from B to A. So we have to somehow explain how these 2 ideas are related. But I hope you see that once we do prove this proposition, then what this proposition really says, once I wrap it all in these nice less than or greater than or equal to signs, is that my definitions actually support saying the size of A is greater than or equal to the size of B, if and only if the size of B is less than or equal to the size of A. Now, I think thinking about why this proposition is true is actually very instructive in terms of thinking about what onto and one-to-one mean and how they relate to each other. So I am going to go ahead and prove this here. So there are 2 pieces here. 1 implies 2, and 2 implies 1. So let's start with 1 implies 2. I should note, by the way, before I get too deep into this proof, what I said here is exactly equivalent to if I had said there exists an onto function f from a to b if and only if there exists a one-to-one function g from b to a, and so our normal proof would be broken into a forward arrow and a backward arrow piece that's just now being called the 1-to-2 piece and the 2-to-1 piece, which we'll do next. Okay, so we're going to suppose one is true, so that is suppose f from a to b is onto. And now what I need to do is I need to show you that there's in fact a one-to-one function from b to a. Now, here's my outline of what it is I'm going to do. I'm going to note this function's already onto, but it might not be one-to-one. And so in particular, this might not be a bijection. But what I'm going to do is I'm going to restrict the domain so that it becomes a bijection, as we've argued before that it is always possible to do. Then I'm going to write down the inverse, which note is a function that goes from b to a. So that's ultimately how I'm going to swap b and a between f and g, as I'm going to write down the inverse. And then I'm just going to throw the rest of a back into the codomain. So let's write that down. So for each element of the codomain, I'm going to choose one element of the domain that maps to it. That's always possible because the function's assumed to be onto. And I'm just going to go ahead and name that thing that I chose. Namely, if little a is the thing I choose to go with little b, then I'm going to denote that little a by g of b. Now, note here, this really does involve a choice. I really am actually making a choice for every element of the codomain, and it might be that for every element of the codomain, there are lots of elements of the domain that map to it. But that's fine. I don't need to show that there's a unique function, g from b to a, that meets this property. I just need to show that there's one. So I'm going to make these choices, and as far as I'm concerned, we can make these choices completely randomly as long as I decide for every little b and big B, a little a and a that maps to it. So now we're going to do the restricting the domain part. I'm going to let a prime be the collection of elements of a that I've actually chosen for some b. This is, if you prefer, you could write this as the set of g of b for b in b. That would probably be a little bit cleaner, but it's a little less clear what's going on. Basically, all the a's I chose, I put in a prime. All the a's I didn't, I throw away for now. So now, by construction, once I drop all of those a's I didn't use out of the domain, this function is now one-to-one. Because a prime consists of exactly one element that maps to every element of b. And so because this function is a bijection, it has an inverse. And that inverse is also a bijection. Right? The inverse of a bijection is definitely a bijection. And so, in particular, this f squiggle inverse is one-to-one. And all I wanted to show, remember, is that there's a one-to-one function from b to a. This is, in fact, a one-to-one function from b to a subset of a, but I can go ahead and fix that by making the codomain bigger. Namely, I'm just defining my function g here to act as f twiddle inverse, but instead viewing the codomain as a instead of a prime. And now, since f twiddle inverse was one-to-one, because it was a bijection, so is g. In particular, what's that saying? No two distinct elements of b map to the same place in a prime, so if I apply the same function, no two elements of b map to the same place in a. So this is because, this implication that because f twiddle inverse is one-to-one, so is g, that's because I'm using the formula f twiddle inverse here for my function g. So that was 1 implies 2 here. We now have to do 2 implies 1. So namely, I have to show you that if there's a one-to-one function from b to a, then in fact there's an onto function from a to b. Now, just like the previous proof, the trick here is going to involve restricting the domain and codomain so that I can make this thing a bijection, then write down its inverse, and then futz with its inverse a bit, and then get back to something to give us our other function. So, if you want to make sure you understood the previous part, this would be a great time to pause and try and write down a proof of this direction, because it's not exactly the same proof, but it's a very similar proof, and I think, in fact, this one is a little bit easier than the direction we've already done. why is it easier? The reason why this version ends up being easier is that this function g is already one-to-one, so the only problem is it might not be onto. But onto-ness is a lot easier to fix than one-to-oneness, because remember, we can always just replace the codomain with the image, and that will turn any function that we start with into an onto function. So by our usual construction, this thing has become onto, but it was already assumed to be one-to-one, certainly still is one-to-one, because I didn't mess with the domain at all, and hence g twiddle is a bijection. And, like before, since it's a bijection, it has an inverse. So we've got this inverse that goes from a prime to b. Remember that because it's an inverse, it's both one-to-one and onto. And then let's remember what it is we're trying to do. We started with a one-to-one function from b to a, that was g. We now have an onto function almost from a to b, except our onto function is actually from a prime to b. And so in order to finish this, I need to figure out how to replace this a prime with an a. Now, before what I did basically is say, well, I'll just replace the set with a thing I want and just write down the same formula. We absolutely cannot do this here. Why can we not do that? We can't do this because g twiddle is only defined on a subset of a. It's not defined on all of a. And so what I have remaining to do is show that somehow, because there's an onto function from this subset of a to b, there's also an onto function from all of a to b. And I know that this is very convoluted and hard to follow, but that statement actually should be very intuitive, because basically, I could send all the elements of a that aren't in a prime anywhere I want, and it won't change the fact that this function is onto. Why not? Because there's already something that maps to every element of b, and so I could send all the other elements to whatever element of b I like, and that'll work out. So that's the kind of thing I really don't want to write down in a proof, though, because it sounds sort of wishy-washy, so I would really like to write this down in a very specific way. And to do that, I'm going to pick a particular element of b. All I'm doing here is choosing an element of b. There could be lots of them, whatever, I'm just going to choose one of them. And what am I going to use this element for? I'm going to use this element so that I can define a function that's actually defined on all of a. So the g twiddle inverse is very close to the thing I want, so I'm going to keep that exactly. If I have an a where g twiddle inverse of a makes sense, I'm just going to use that. And so what's the b naught for? I'm just going to send everything else to b naught. And now, the fact that f is onto follows from the fact that g twiddle inverse was onto. And that proves both directions. It gives us, in fact, a fairly explicit construction to transform an onto function in one direction to a one-to-one function in the other direction, and likewise a one-to-one function in one direction to an onto function in the other direction. So even though their definitions are very, very different, one-to-oneness and onto-ness are, in a way, very closely linked, because it turns out that the existence of a one-to-one function in one direction is exactly equivalent to the existence of an onto function in the other direction, which is not at all something that I think is immediately clear, even after a fair amount of contemplation and a fair amount of work with these definitions. Probably this is not something you have ever thought to think about before. But with that, we have fixed our over-definition problem. Namely, this symbol now behaves as it should. And we can move on, right? But sadly not. I need to point out there's actually a far more insidious problem with over-definition that might sneak by if we weren't careful. And that has to do not with what happens when you flip this sign in this way, but what happens when you know, for example, that A is both greater than or equal in size with B and less than or equal in size with B. Namely, we would assume that if something is both greater than or equal to something and less than or equal to something, then it should actually be equal to it. And this result, by the way, the fact that what I'm about to write is true, is called the Cantor-Bernstein theorem. And so what it really says is if the size of A is greater than or equal to the size of B, and the size of A is also less than or equal to the size of B, then in fact the size of A is equal to the size of B. Now, if I write it like this, it's really tempting to say, that is so obvious, I can't believe that not only one person, two people got their names on this. This is a thing we've known since the first grade. But what I want to remind you is that these symbols do not mean the same thing we're used to thinking about them with real numbers. We literally just defined what these symbols mean for sets earlier in this video. And if I actually write out what this is saying in terms of our definition of greater than or equal to, less than or equal to, and equal to, this actually says something that I think is quite surprising. So, pause real quick. Try and translate this. Translate this to what this is saying about functions before I write it down. What this is saying is if there exists an onto function from A to B, and there exists a one-to-one function, A to B, then these two together imply the existence of a bijection from A to B. And while this statement looks kind of trite and obvious, this statement looks kind of terrifying, because what I have here is two functions which have opposite properties. One's onto, one's one-to-one. And then from those two functions, somehow, in some mysterious way, we're producing a third function that has both of those properties. Please note it would be easy to think that what these two things together are saying is I've got a function that's both, in which case, great, it's a bijection. But that's not what this is saying. I don't know that I have a single function that's both. I know that I have one function that's onto, and one function that's one-to-one, and somehow I have to put those together to get a function that's a bijection. Now, it turns out the proof of this is actually rather daunting, and I'm not going to summarize it for you here. It's certainly something where if you just Google the name, you can find plenty of people going over the proof. And it's definitely something where if you're motivated and you're really curious about why this is true, you can definitely figure it out. But it turns out that this is really at the very core of what's going on with all of the sizes of infinite sets. And the fact that this is true, together with this previous result that we proved, is what lets us really work with infinite sets and sizes of infinite sets in a way that makes our lives easier, and lets everything end up, at least sort of, making sense. With all of that, I'm now able to prove the thing I promised to prove at the beginning, which is that the size of the positive integers is strictly less than the size of the reals. In fact, I'm going to prove something that's even better. I'm going to prove that the size of the integers is actually strictly less than the size of just the closed interval 0, 1. This is a subset of the real numbers, and so if I prove this is already bigger than the integers, certainly the set of real numbers is bigger than the integers. With all of this setup, I know what I have to prove. The first thing we need to do is show that the size of the positive integers is less than or equal to the size of the closed interval 0, 1. Why? Because that's literally our definition of strictly less. Namely, strictly less, our definition was less than or equal to plus not equal to. So I'm going to do less than or equal to first. And so to do that, I need to give a one-to-one function from the positive integers to the closed interval 0, 1. Now, it might actually take you a bit to think of such a function, because, of course, the positive integers don't really naturally sit inside the closed interval 0, 1. But here's a way to do it, namely, just send each positive integer to 1 over that positive integer. So for every positive integer, 1 over n is definitely between 0 and 1, inclusive, and every n definitely goes to a different number between 0 and 1. And so this function is one-to-one. That shows us that in our language, the size of the positive integers is less than or equal to the size of the closed interval 0, 1. Second thing up, we need to show that the set of positive integers has a cardinality that is not equal to the cardinality of the closed interval 0, 1. As you might have guessed, this is the harder part. Because once we translate this, what this is really saying is we need to prove that no function from the positive integers to the closed interval 0, 1 is a bijection. And note, showing a particular function is not a bijection is no problem. This function, for example, the one we wrote down before, is definitely not a bijection. Because, for example, 2/3 is in the closed interval 0, 1, but it is not in the image of this function. No problems there. However, what we're saying here isn't a particular function isn't a bijection. It is that no matter what function you write down, it's never a bijection. So let me be a little more precise. What am I actually going to show you? I'm actually going to show you that no function from the positive integers to the closed interval 0, 1 is onto. I remember vividly when I was in grad school, one of the faculty members told me, there's only about a dozen ideas that show up in proofs and amount for about 98% of all the proofs that show up in all the papers. And it's the proofs that really deviate from those dozen or so ideas that need something fundamentally different than those that end up being famous. This is such a proof, because it seems very difficult to figure out how we're going to take some arbitrary function from the positive integers to the closed interval 0, 1 and show that it's not onto. In fact, I don't even think this statement is at all intuitive. I think if you were forced to guess, I think you would guess that you could write down an onto function here. And it ends up being rather perplexing that it turns out that actually it's not possible. But this is how Cantor proves this. So we're going to suppose f from the positive integers to the closed interval 0, 1 is a function. There are two ways to do this, by the way. You could suppose for sake of contradiction that this function is onto and then show it's not. But I don't need to do that. I'm just going to start with any function, and then I'm just going to show you it's not onto. Okay, so here's what I'm going to do. I'm going to write out the numbers that each number maps to. So 1, 2, 3, 4, 5, and so on down the line. And so I'm going to write them down in decimal. And so we're going to have our list of all of these things written out. Now what I'm going to do is I'm going to go ahead and define a number. And I'm going to call this number alpha. And I'm going to show you how I'm going to make alpha. So I'm going to start with 0 point, so I'm still going to make it be inside this interval. And I'm going to look at this 7, and I'm going to write down here for alpha the digit that's one more than that. So because this is a 7, I'm going to write down an 8. This next one, that's a 2, so I'm going to write down a 3. This is a 3, so I'll write down a 4. This is a 3, so I'll write down a 4. And this is a 3, so I would write down a 4, and so on. And by the way, if I happened to run across a 9 on the diagonal, I would write down a 0 as the next digit. And so here I've defined a very precise real number. And I want to make two claims about alpha. My first claim about alpha is that alpha is in the interval 0, 1. Well, that's not so hard to see. I started with 0 point. That was the first thing I said I was doing in my definition of alpha. And so any number that starts 0 point and then some digits, it's definitely in the interval 0, 1. The second, and this is maybe the more impressive and important one, is that alpha is definitively not in the image of f. And the heart of this proof is in understanding why the alpha that I defined here is definitely not in the image of f. And so here's the argument. This first one here, well, alpha can't be f of 1. Why can't alpha be f of 1? Because f of 1 has a 7 in this slot, whereas alpha has an 8. And the not-so-profound fact we're using here is that if two numbers have different decimal expansions, they're different. So this 7 and this 8 are different. So this thing is definitely not f of 1. And note, even though I'm just showing you this construction in one particular example here, this would always work because I said the way you choose this first digit is you look at f of 1 and then you change that digit by 1. And so alpha is never f of 1. For similar reasons, I claim actually alpha is never f of 2. So why is alpha never f of 2? Well, because f of 2 has a 2 in the second slot, but alpha has a 3 there. And again, that's just the digits in this particular example, but I said the way you choose the second digit is by adding 1 to the digit in f of 2. So alpha is never f of 2. But note, by the same logic, alpha is never f of 3, and it's never f of 4, it's never f of 5, and so on. Indeed, alpha differs from f of n in the nth decimal place. And so, in fact, what's happened here is that I've described a way to, from just the function f, write down an alpha that's never in the image of f. And I've done that by arranging it so that alpha's nth digit is never the same as f of n. And so, in other words, I've made it so that alpha is not f of 1 because they disagree in the first digit, not f of 2 because they disagree in the second digit, not f of 3 because they disagree in the third digit, and so on. And so, in particular, alpha is not f of n for any integer n, and so alpha is not in the image of f. And because alpha is not in the image of f, well, what does that tell me? That tells me that f is not 1, 2. And that completes the proof. There can be no bijection between the positive integers and the real numbers between 0 and 1. Now, there are all kinds of mind-bending things you can note about this. So one of those mind-bending things is, okay, so alpha is not in the image of this function. But I can actually do the Hilbert's hotel thing where I slide all of these numbers down by 1, so I actually make 2 map to this number, 3 map to this number, 4 map to this number, and then just make 1 map to alpha. And now I've got a different function. It's not f, but I've got a new function. And the new function's image is in fact exactly what the image of f was, but I've thrown in alpha. And so it might seem like, wait, isn't that going to do it? But no, because the same construction will spit out something, say, beta, that's not in the image. And I can keep adjusting this, and so I can throw beta into the image, and then throw a gamma into the image, and then see how many letters of the Greek alphabet I know before I run out. But I can just keep going with making the image bigger and bigger and bigger by throwing something into the image that wasn't there before. But what this proves is that no matter how long I do that for, I'm never going to be able to get a function which includes all of the numbers between 0 and 1. As a last note for today, I want to point out that actually, even beyond everything we're talking about here, this actually shows us a really fundamental thing about the real numbers that was not clear before. Namely, it's not possible to list the numbers between 0 and 1. Now, at first that might seem like a sort of silly observation because, of course, I can't list the numbers in any infinite set. But I claim actually, as long as you're allowed infinite lists, you can definitely list things like the prime numbers, for example. 2, 3, 5, 7, 11, ... This is a list of the prime numbers. So I can list the prime numbers. 1, 2, 3, ... That's a list of the positive integers. So I can list the positive integers. But if I look at what this function from z plus to the interval 0, 1 really is, it's really just a list. This is the first thing, this is the second, this is the third, this is the fourth, this is the fifth. And so what I'm saying is if I put a list separated by commas, starting with some real number and then continuing down the line, I'll never include all of the real numbers. The fact that you can't list the real numbers even in the interval 0, 1 in this way is really at the heart of what we mean when we say that this set is more infinite than the positive integers. So with that, we've proven that really honestly and truly, this size of the positive integers is a different thing than the size of the real numbers. This is strictly larger, and we now know what that means. But there are lots of unanswered questions. So, for example, I showed you that the closed interval 0, 1 is strictly larger than the positive integers. That's a subset of the real numbers. So you know that that means that the positive integers are smaller than the closed interval 0, 1. But you might ask, well, is the closed interval 0, 1, is that the same size as the real numbers? I mean, that's not clear, right? Maybe the closed interval 0, 1 is strictly in size between the positive integers and the real numbers. We're not quite sure. I also keep teasing this idea that the rational numbers have to fit in one of these boxes, but we haven't said which box yet. And so next time, we're going to try and sort those things out. So we're going to try and figure out, do intervals, closed, open, and so on, do they live in this box or a different box? Do the rational numbers live in this box or this box? And we'll talk about some techniques that use some of the methods that we've learned today to streamline showing that two sets have the same cardinality without having to write down a bijection between them. All right, but that's plenty for today. We'll pick up here next time with more about the hierarchy of infinite sets and where the sets that we know and love live in that hierarchy. But that's all for now. I'll see you next time.